Right now, deep in the interstellar medium, an isolated stellar corpse is ripping the fabric of the universe into a swirling whirlpool. Recent telemetry data has captured a rogue neutron star moving at blistering speeds, but it is not just flying through the cosmic void, it is violently dragging reality itself along for the ride. The localized spacetime around this object is twisting so severely that light and matter are being forced into a gravitational tornado. This is not a simulation, this is raw, newly analyzed data streaming down from orbital X-ray observatories, looking at a phenomenon we barely believed could exist in such a chaotic state. We are seeing a glitch in the cosmic mechanics, a place where the standard rules of gravity are breaking down and being replaced by something far more turbulent. But the sheer scale of the spatial distortion points to a massive contradiction in our understanding of stellar collapse. How can a dead star, no larger than a medium-sized city, generate a temporal and spatial vortex powerful enough to shred the fundamental geometry of the vacuum? The answer lies in a paradox, hidden deep within the latest spectroscopic analysis, one that will fundamentally alter how we view the invisible forces governing the cosmos. As we dive into this raw data to unravel exactly how this rogue star is weaponizing gravity, if you want to stay at the forefront of these deep space discoveries, consider subscribing to the channel to keep exploring the frontier of the universe with us. The anomaly begins with the trajectory. When independent researchers first aimed their instruments at this particular region of the sky, they were not looking for a spacetime vortex. They were mapping the thermal glow of cold molecular clouds floating in the galactic halo. But piercing through that veil of hydrogen gas was an intensely bright point of X-ray emission, moving at a velocity of over 1,000 kilometers per second. To put that staggering speed into perspective, at that rate you could travel from the Earth to the Moon in under 7 minutes. Objects simply do not move that fast through the galaxy, unless they have been subjected to an apocalyptic event. This immense speed immediately classified the object as a rogue star, an exile violently kicked out of its original binary system or host cluster. But the speed alone is not what caught the attention of the scientific community. It is what the star is doing to the space around it as it plows through the dense molecular cloud. As the neutron star encounters the stray gas and dust of the interstellar medium, its immense gravitational field captures the material, pulling it inward to form a temporary accretion disk. This disk should, according to classical Newtonian physics, form a flat, orderly ring of orbiting material, slowly spiraling inward until it crashes onto the surface of the star. But the data reveals something entirely different. The light curves generated by the incoming X-ray photons show that the accretion disk is not flat. It is violently warped, completely unstable, and actively tearing itself apart into concentric rings. The material is not just orbiting the star, it is being forced into a three-dimensional spiral, corkscrewing inward as if being pulled down an invisible drain. This observation points directly to a phenomenon known in advanced theoretical physics as the Lense-Thirring effect, commonly referred to as frame dragging. To understand the sheer violence of what is happening, we must temporarily set aside our everyday understanding of space as an empty, static stage where events take place. In the realm of general relativity, space and time are fused into a single, dynamic, flexible fabric. When a massive object exists within this fabric, it creates a depression, like a heavy bowling ball resting on a trampoline. This is classical curvature, which we experience as gravity. But what happens when that impossibly dense object begins to spin? A neutron star is the crushed core of a massive giant that ran out of fuel and collapsed under its own weight. A mass roughly equivalent to 1.5 times the mass of our Sun is squeezed into a sphere barely 20 kilometers across. Because of the conservation of angular momentum, the same physical law that causes a figure skater to spin faster when they pull their arms inward, the collapsing core accelerates to mind-bending rotational speeds. The telemetry suggests this particular rogue star is rotating on its axis hundreds of times every single second. Its surface is moving at a significant fraction of the speed of light. And because the star is so dense and its gravitational field so incredibly powerful, its rapid rotation physically grips the fabric of space-time. As the star spins, it drags the surrounding vacuum of space around with it, much like a spinning spoon drags thick honey inside a jar. This means that near the surface of the rogue star, it is physically impossible to remain stationary. Even if you fired rocket engines with infinite power to hold yourself completely still, the actual space you occupy is being swept along in a continuous, violent circle. The space itself is rotating. This is the vortex. This brings our attention to a critical contradiction in the orbital telemetry. The incoming matter captured from the surrounding molecular cloud has its own independent angular momentum. It wants to orbit the neutron star on a specific plane, dictated by the angle at which it was captured. However, the rapidly spinning neutron star has an equatorial plane of its own, and the two planes do not align. The matter is trying to orbit one way, while the swirling vortex of dragging spacetime is forcefully demanding that the matter orbit along the equator. This creates an intense physical conflict, a tug-of-war between the inertia of the gas and the twisting geometry of the universe. The result is an effect known as the Bardeen-Pedersen resonance. The inner regions of the accretion disk, sitting closest to the star, are entirely dominated by the twisted spacetime. The geometry of the vortex violently forces the inner disk to align with the equator of the star, but the outer regions of the disk, located further away, where the frame-dragging effect is weaker, stubbornly remain in their original orbital alignment. The data reveals the catastrophic consequence of this disagreement. The accretion disk literally snaps. The sheer twisting force of the localized space shears the disk into distinct, separate rings. The transition zone between the outer disk and the inner disk becomes a region of unimaginable friction and shock waves. Gas crashing into gas at tens of thousands of kilometers per second heats the material to hundreds of millions of degrees, causing it to emit the intense X-ray flashes that our orbital observatories are currently intercepting. But looking deeper into the light curves, the analytical data exposes a secondary layer to this cosmic mystery. The separate torn rings of the accretion disk are not just sitting there, they are wobbling. Just like a spinning top that begins to sway as it loses momentum, the twisting space causes the inner ring of superheated plasma to precess around the star. We can actually see this wobble in the raw numbers. The X-ray emission does not arrive in a steady stream. It fluctuates, growing brighter and dimmer in a rhythmic pattern over the course of mere milliseconds. We refer to these rapid fluctuations as quasi-periodic oscillations. When independent analysts process the timing of these arriving photons through complex mathematical models called Fourier transforms, they can extract the precise frequencies of the wobble. The numbers are staggering. The inner ring of plasma is completing a full precessional wobble dozens of times per second. This frequency serves as a direct, undeniable measurement of the strength of the frame dragging effect. It is a ruler by which we can measure the twisting of spacetime. And this is where the major anomaly presents itself. The frequency of the wobble observed in the data is far higher than standard models of neutron star physics predict. According to our current understanding of structural density, a neutron star of this estimated mass should not be able to grip spacetime this fiercely. The vortex is too powerful. This discrepancy forces us to ask a profound question about what exactly resides inside the core of this wandering stellar corpse. To solve this, we must look at the unseen architecture of the star itself. A neutron star is not a solid rock. It is a highly stratified object with a rigid crystalline crust made of compressed iron nuclei. But beneath that crust, the pressure becomes so extreme that atomic structure completely breaks down. Electrons are violently crushed into protons, neutralizing their charge and leaving behind a fluid of pure neutrons. Deeper still, theoretical physics suggests the existence of a state of matter known as nuclear pasta, where the nuclear force contorts the particles into long tubes and flat sheets. At the very center, the absolute core of the star, the pressure reaches levels that challenge the limits of quantum mechanics. Some models suggest the core remains a superfluid of swirling neutrons, flowing without any friction whatsoever. Other more radical theories propose that the neutrons themselves are crushed out of existence, dissolving into a soup of free-roaming quarks, the fundamental building blocks of matter. The excessive frame-dragging effect observed in this rogue star might be the first observational evidence pointing toward a highly exotic core. If the core of the star is compressed into a pure quark plasma, its mass distribution would be altered. The core would be denser and more compact, altering the moment of inertia of the entire star. This subtle shift in how the mass is distributed from the core to the crust would dramatically amplify how tightly the star grips the fabric of space. The violent vortex we are observing might not just be a consequence of the star spinning, it could be a direct telegraph from the most extreme state of matter in the universe, whispering the secrets of quantum gravity through the chaotic tearing of an accretion disk. But the mystery deepens when we examine the spectroscopic signatures embedded within the X-ray light. Not all X-rays are created equal. When the superheated plasma in the inner ring of the torn disk collides, it causes trace elements of iron within the gas to fluoresce, emitting X-ray photons at a very specific energy level. In a laboratory setting on Earth, this iron emission always occurs at exactly 6.4 kilo-electron volts. It is a precise fingerprint of the element. However, when we intercept the photons originating from the gravitational vortex of the rogue star, the energy fingerprint is horribly distorted. The peak of the emission is smeared out, stretched across a wide range of energies. This spectral smearing is the ultimate proof of the extreme physics at play, and it is driven by two simultaneous relativistic effects acting on the light. First, we have the Doppler effect caused by the incredible velocity of the spinning plasma. As the torn inner ring orbits the star within the spacetime vortex, one side of the ring is hurtling toward us at nearly a third of the speed of light, while the other side is racing away. The photons emitted by the side moving toward us are compressed, giving them more energy and shifting their signature toward the blue end of the spectrum. Conversely, the photons from the retreating side are stretched, losing energy, and shifting toward the red end. This is known as relativistic beaming, and it makes the approaching side of the disk appear vastly brighter than the receding side. But the second effect is even more profound, and it is entirely independent of motion. It is gravitational redshift. The photons emitted by the iron atoms deep within the vortex must expend a massive amount of energy simply to climb out of the gravitational well of the neutron star. They are fighting against the immense curvature of space. As they lose energy escaping the gravity well, their wavelength stretches, shifting the entire smeared profile toward lower energies. By carefully analyzing the shape of this distorted iron fingerprint, researchers can map the exact dimensions of the spacetime vortex. The wider the smear, the deeper the vortex. The data from this rogue star shows a spectral line so broad and deeply shifted that the inner ring of torn plasma must be orbiting mere kilometers above the surface of the star. It is practically scraping the crystalline crust. This is a region where the fabric of spacetime is stretched almost to the breaking point. If the plasma were to move just a fraction closer, it would cross the boundary where no stable orbit can exist, forced to plunge directly into the surface of the dead star in a brilliant flash of nuclear fusion. But what drove this star out into the cold wilderness of the galactic halo in the first place? The extreme velocity of the rogue provides a crucial clue about its violent birth. Neutron stars are born in the hearts of dying supergiants during a catastrophic event known as a core collapse supernova. When the core of the giant star implodes, the outer layers of the star fall inward, hit the incredibly dense new neutron core, and rebound outward in a colossal explosion that outshines entire galaxies. In a perfectly symmetrical universe, this explosion would expand evenly in all directions, and the newly born neutron star would remain exactly where its parent star lived. But nature is rarely perfect. The telemetry and trajectory of this rogue suggest that its birth was fiercely asymmetrical. Deep within the exploding star, vast plumes of superheated plasma and turbulent neutrino storms boiled and churned. If one side of the supernova explosion erupted with even slightly more force than the other, the resulting shockwave would act like a cosmic rocket engine, kicking the core in the opposite direction. To achieve the velocity of over 1,000 kilometers per second observed in the current data, the supernova explosion must have been heavily lopsided, perhaps driven by an ultra-powerful magnetic field that funneled the energy of the explosion out through the poles of the dying star. This asymmetric kick violently ejected the newly formed star from its birthplace, sending it on a solitary journey across the galaxy. For millions of years, it traveled in darkness, an invisible, rapidly spinning magnet sweeping through empty space. It was only when it blindly plowed into the thick molecular cloud that its invisible vortex found material to grab onto, lighting up the darkness and revealing its presence to our telescopes. The implications of this discovery are sweeping through the astrophysical community. We are witnessing the mechanics of extreme gravity in an entirely new context. Usually, to study frame dragging of this magnitude, astronomers look towards supermassive black holes at the centers of distant galaxies. These black holes, weighing billions of times more than our Sun, are surrounded by massive, ancient accretion disks that shine brilliantly across the universe. But black holes hide their most extreme physics behind an event horizon, a boundary beyond which nothing, not even light, can escape. The singularity at the center of a black hole is forever shielded from our view. A neutron star, however, has no event horizon. It possesses a hard physical surface. The spacetime vortex generated by this rogue star is entirely visible. We can watch the torn rings of plasma interact with the magnetic fields anchoring the crust. We can measure the exact point where the twisting of space forces matter into an unstable plunge. This rogue star is serving as an exposed laboratory for the strongest gravitational fields in the visible universe. This observation also forces us to rethink our models of galactic evolution and the life cycle of binary star systems. It is estimated that millions of unseen rogue neutron stars wander the outer reaches of our galaxy, kicked out of their original homes by asymmetrical supernovae. Until now, they were considered completely dark, undetectable ghosts haunting the galactic halo. But if rogue stars can capture enough stray gas from the interstellar medium to form highly energetic, torn accretion disks, then they might be responsible for unexplained transient flashes of X-ray radiation frequently observed in empty regions of space. What we once thought were distant galaxies or flaring dwarf stars might actually be the brief, violent awakenings of dark wanderers passing through stray clouds of gas. Furthermore, the mechanics of the torn disk provide an unexpected testing ground for one of the greatest unresolved conflicts in modern science: the incompatibility between general relativity and quantum mechanics. General relativity perfectly describes the smooth, continuous warping of spacetime on a macroscopic scale. Quantum mechanics perfectly describes the discrete, localized behavior of particles on a microscopic scale. But in the boundary layer, mere kilometers above the surface of this rogue star, both theories must operate simultaneously at maximum intensity. The tearing of the accretion disk is driven by the smooth geometry of spacetime, but the resulting friction, extreme heat, and X-ray emission are driven by the quantum interactions of subatomic particles colliding at relativistic speeds. If there is a flaw in general relativity, if the fabric of space begins to behave differently when stretched to these absolute limits, the signature of that breakdown will be hidden in the exact frequencies of the quasi-periodic oscillations we are currently tracking. As we continue to monitor the telemetry streaming from this dark wanderer, we are faced with an approaching inevitability. The localized molecular cloud the star is currently passing through is not infinite. Eventually, the high-velocity star will break out the other side of the gas cloud, leaving the dense region behind. When that happens, the supply of fresh matter falling into the vortex will be completely cut off. The torn rings of the accretion disk will finally lose their orbital energy, plunging violently onto the crystalline surface of the star in a massive burst of radiation. The X-ray beacon will extinguish, and the rogue star will once again fade into total darkness, continuing its endless journey through the void. The space-time vortex will still be there, spinning furiously, dragging the empty vacuum along with it, but we will no longer have any matter to illuminate its twisted shape. This makes the current observation a fleeting, incredibly rare window of opportunity. If we can extract the full truth from this data before the star goes dark, we might finally unlock the definitive structure of the neutron star core, proving whether the universe allows for the existence of pure quark matter. We might confirm whether the Bardeen-Pedersen effect behaves exactly as predicted in strong field gravity, or if unknown corrective forces must be added to our mathematical models. The torn disk, the wobbling plasma, the smeared iron lines, and the extreme velocity of the star are all pieces of a much grander puzzle that speaks to the very origins of mass, gravity, and the ultimate fate of collapsed matter. If you are fascinated by the intricate, extreme mechanisms governing our universe and want to help boost scientific deep dives like this, leaving a like on the video greatly supports the research and analysis required to bring these complex space phenomena to light. The existence of this gravitational vortex serves as a powerful reminder that the universe is not a static, empty void filled with isolated objects. Space is a physical medium, capable of being bent, twisted, torn, and dragged by the entities that inhabit it. The rogue neutron star is not just traveling through space. It is fundamentally altering the geometry of the universe in its immediate vicinity, turning the vacuum into an active participant in the destruction of matter. As we refine our observational techniques and deploy next-generation instruments capable of greater spectral resolution, we will undoubtedly find more of these dark wanderers, each one offering a new perspective on the invisible forces that bind the cosmos together. For now, we continue to watch the data, waiting to see what the wobbling rings of superheated plasma will reveal next about the ultimate nature of gravity.